In the earlier video what we were discussing was a crossbar and how it can be used as a packet switch, and we specifically analyzed if we can actually put the packets in the input queue, because there are bound to be conflicts when more than one packet would like to go to the same output port. Okay. And in that case only one of them can go out, other one cannot go out if the speed up factor is 1. So, we defined the speed up factor, we defined input queuing, we defined output queuing, which happens when speed up factor is equal to number of ports. And then of course, we compared these two and figured out what will be the maximum throughput which we will be able to get, especially input queue has a limited throughput, you cannot achieve 1, while output queuing you can get the maximum throughput. Okay. The buffers at the output side will take care of the staggering, but on an average the same number of packets will be coming for each outgoing port. So, the queue will always remain stable for output queued system. For input queued, then we thought, okay, can we modify a strategy and then further improve the throughput. We in fact investigated that and came up with an idea that if the load crosses a certain threshold, then I should move over to dropping the packets which are contending and which are not successful in the input queuing system. So, that was the analysis which we did, but that was still a single crossbar. If I want to build up a very large packet switch, then what is going to happen? I need a very large size crossbar. I also need a separate centralized controller which has to do very fast comparison of all the headers, scheduling them and then configuring the switch. So, the load on this particular switch controller will be pretty much high. In circuit switching system, if you can recall, what we actually had done is we have tried creating multiple stages, multiple switches, smaller ones to be used, and still build up a very large switch. Now, can I do the same thing in the packet switching? That is the question. Yes, we certainly can do that, but then how the load on the controller will go down. So, one possibility is that I may actually use smaller switches. I connect them in multiple stages. Maybe I can take up an idea of a closed network kind of thing. Now, what I do is I do not actually use centralized controller. These are like all small crossbars, all of them. So, there is certain input. So, at each input port I can actually identify, I can put a board, an electronic board. This is going to actually analyze all the packet which is coming from the input side, and once the packet has been analyzed, it will figure out from there that to which outgoing port a packet has to go. Once it knows it has to go to a certain outgoing port, it should be able to insert in front of that packet something called tag. Okay. And based on this tag will contain certain bits or characters or bytes, and as this packet now is being injected, every switch will have at the input an interface board which will then analyze this particular tag and decide to which outgoing port it has to go. Basically, it will tell to which particular switch it should be handed over. This particular switch will now analyze a different part of the tag, will decide where it should go. So, basically the complete path which this packet will take through this matrix, through this switch, can be decided by the tag which is going to be inserted. Once the packet reaches at the output, I can remove the tag and then let the packet go through as it is out. Once I do this, I do not require a centralized controller. So, every interface, every input actually has this small controller which inserts the tag after computing it, and then each switch is independently controlling itself. It has its own dedicated controllers which will analyze the tags at the input and based on that start routing the packet. There is a possibility that you may end up in getting multiple packets here which would like to go to the same port. So, if that possibility happens, either you have to drop the packet or you have to buffer it. Okay, but what kind of network I would like to have? if I am going to have network which will have more than one path, for example closed network, we did a 3-stage close, and from one place to another place I was actually having multiple routes. So, from one input I can go to via 3 routes. Now, that is where the problem which will come in the tag switching. So, normally these kind of networks should not be preferred, but of course they certainly can be used. Okay. But somehow you need a coordination that to which outgoing port I should actually route the packet to, because once it will reach here there may be conflict with this, there may be conflict here, there may be conflict with equally likely probability. So, these can be used, but these are going to be cumbersome. So, a good idea is that if I have deterministic path through which a packet will follow when I will inject it into the switch is very important. So, we actually use a category of switches which are known as Banyan networks for routing the packet switches. These are also multi-stage packets, multi-stage switches, but the most important thing, let me define what the Banyan network is. So, we will have switches. So, this can be B by B kind of thing, or N by A by B, or whatever you want, or a 2 by 2 also. But once I have this, so I will contain multiple of them. So, you will be, the condition is that you should be able to go from any input to any output. So, from any input I should be able to go to any one or any output which I want, and there should be exactly one path from this input to every other output. So, take any input output pair and there should be exactly one path. So, let us try to create one such switch. So, I am actually taking it say 8 by 8 system, and let us see the 8 outputs and 1 input, how I am going to create this kind of switch. So, this in fact gives the structure that how the Banyan network is going to be formed. So, I am taking 2 by 2. So, I am technically creating what we call a demultiplexer tree. So, from one input I should be able to go to any one of the 8 outputs. So, I am even not bothered about the second one. So, if I can go from one, I can also go from the second one to the 8 outputs. So, I will split and take it into 2 switches. Then there are further 2 inputs. These inputs I will look into this thing later on. And if I can further split this, so I am able to get a demultiplexer tree. There is exactly one path from this input to every other output. From this input to all the 8 outputs, there is exactly one path. What about the second one? If I do this, of course, from this again there is exactly one path from this input. What is going to happen if I have another switch? I can create one here and one here. Again there is exactly one path. I have actually essentially this demultiplexer tree of these two have these elements in common. Okay. So, I have just plug it in. I can similarly actually put few more. Okay. So, I create another demultiplexer tree and keep these 4 elements as common. Okay. So, from here also I created a demultiplexer tree. I can use this and also a demultiplexer tree. So, in general for this one, for example, it is a log 2 of 8 number of stages which will be required. So, which is 3 in this case, 3 stages. Each stage will contain 8 by 2, 4 switches, and each switch will be of 2 by 2 crossbar. So, from every input to every output there is a unique path which is available. I will make slight change here. What I will do is I will keep it as it is. Sorry. So, I have just created a switch of this kind. Now, I am actually now going to put the addresses. So, there are 8 things. So, I am actually taking each will be represented by 3 bits. So, for the first one I will get it 0 0 0, I will make it 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. Now, I can actually push in a packet and I can insert a tag, and the way we will put it that there will be 3 tags. So, the first value of the first bit of the tag will be used by this row, the second will be used by this one, and the third bit will be used by the third row, and based on that whether it is 1 or 0 they will go up and down. So, I can actually make a configuration where it will be 0 1, 0 1, 0 1, 0 1, 0 1, 0 1, 0 1, so if I actually insert for example 0 0 0 from here, then where it will go? Okay. So, at every place I can put a 0 0 0 see and see where it is going. So, if I put a 0 0 0 here, the packet will be looking at the first bit, will be moving to this 0, coming all the way here, the second bit will decide it will again come here, third bit will decide it is coming here actually. So, if I insert a packet with tag 0 0 0, it is going to go to the output 0 0 0, but if I insert the same tag here, then what is going to happen? This one will be now routed to the upward thing which will come here. So, first 0 it will bring it here, second 0 will bring it here, and third 0 will bring it here. So, this 0 0 when inserted here will actually reach here. So, I just need a unique tag. If I know this port, I know where I am. Based on these two input port and output port address, I should be able to figure out a tag and insert that tag into the packet, and then using self routing the packet will actually ultimately reach here. Okay. So, these kind of networks are what is known as Banyan networks. There is exactly one path from an input to an output. Okay. So, now in this case what actually we are doing, we are taking one packet at a time and doing it. Now, this is not the only way of doing the switching, there is another way, we call it fast, this is known as fast packet switching. There is another method, we call it fast circuit switching. So, earlier we had been doing circuit switching and now we move to packet switching. We should also know what is a fast circuit switching. So, in this case idea is in the network, when I actually have to set up a path, it is basically not one network, there are multiple networks. In a big network there are many switches and each one of them is a switching element. So, normally from the input side I will actually send a small header first, and then after a gap I will send my chunk of bytes which has to go. This header will actually, as it is going to move through, it will keep on setting up a virtual circuit or a circuit for a duration when this data will be passing through. Okay. So, this header will keep on moving, everywhere it is going to be processed. So, gap between these actually will reduce. So, next time the gap will be slightly less, by the time it reaches here the gap will be still smaller, when it reaches in the final it can be very small value. But if this gap actually gets finished up here itself, because the header processing time itself is pretty large, then this burst you will not be able to route through. This is also known as burst switching. What I am talking about is a fast packet switching. The packet is coming and it is being, all packets are of equal length and they are being synchronously moved from one stage to another stage till the end. Okay. So, we are not talking about this one. So, this needs a different kind of switching design. and you have to build up a reservation structure here, but optical bus switch networks, since they will be coming up, so that also is an important thing, but we will not be talking about optical bus switches in this particular part of the course. So, typically these fast packet switching systems, as I told, is going to be Banyan network. So, there are two configurations, one is a Banyan configuration. As I told, if there are two packets, they are trying to go to same single output of a switch, there is a contention. Even if the packet which is coming from here is directed for this one, packet coming from here is directed for this one, there is no conflict for the outgoing port, but they need to go through the same link, they will get blocked. Because of this, the performance of this Banyan networks is not very good, okay, it is actually limited because of this internal link blocking. So, we do have Banyan networks, but people have then invented methods to take care of these kind of conflicts. So, we also have buffered Banyan, we will be looking this into the buffered Banyan analysis in the next week. Then, because even if you do buffering, I can remove these internal conflicts, okay. I can actually somewhat handle it, improve my throughput, but still it cannot go to 100%. So, is it possible when the packets are coming here, they do not actually get into conflict? Remember, even if the packets, all the packets are for different ports, then also they can get blocked in this system. This is not a strictly non-blocking system, okay. While crossbar is a strictly non-blocking system, so you are actually now compromising, you are going from crossbar to this, having a simplified control, implementing self routing, but you are losing on any arbitrary permutation map which can happen from input to output, that will not be possible in this case, okay. In this case, only number of permutations which are allowed will be equal to number of these switches raised power 2, if these are 2 by 2 elements in that case. So, I will do that calculations once I go through this review. So, to sort out this particular thing, there is a mechanism which you can do is, you can actually build up again a similar kind of network, where you put packets for various addresses anywhere, and there is going to be an algorithm which is going to be used, depending on which address is smaller and lower, the packets will be shuffled actually here. So, they will be either, if always the smaller packet will go up, bigger one will go, or the larger address will go here, and so on, they will have a different sorting sequences. I will be able to actually sort out all these packets and they will come in order here, and then if I can do a shuffling and then insert into a Banyan network, there will not be any conflict, all of them will pass through without any problem, there will not be any internal conflict. So far all packets are directed to different outgoing ports. So, this category of networks are known as sorted Banyan. So, technically what you are doing is, you have increased the number of stages in a Banyan network and made it a strictly non-blocking switch. So far if there is no conflict for the outgoing port, okay. So, it will just pass through as it is, but it needs more delay. So, that is another category. Then it is possible that you can actually create disjoint path topologies. So, multiple paths which can be there, and if there is a conflict you actually pass through multiple paths, that also is possible at any point of time. So, this is disjoint path topology basically, base switches. In this case, all the packets which are even having conflict for the output will reach simultaneously to the output port through multiple paths, and once they reach there, they have to be queued up, because all of them cannot be pushed out on the outgoing link at the same time. So, you require output buffering in this case. Then of course, we had already talked about in last time is a crossbar based systems, which are the most versatile because you can create any input to any output kind of possible maps. So, I will give the number of these maps which are possible in crossbar. It is possible to build up TDM based switch fabrics with common memory. So, idea is that all the packets which are going to come in from the input, all of them will be stored in a common memory, and they will be stored at one place and then they will be read out at a faster pace. Okay. So, you can read in sequence, write in sequence and read asynchronously the packets, and the packets will then get switched off to the various outgoing ports. And then of course, you can actually have a shared medium, is basically broadcast and select. So, these are the basic categories, but we will be focusing only on the Banyan this particular configuration. Once you have this Banyan, again I have given you example that if you put 0 0 0 0 0 0, but they move to different outgoing ports. Now, is it possible that if I can use the output port address itself as a tag here. So, from whichever port I will put, it will always reach to the same outgoing port. Yes, that is possible, and these category of switches are known as delta networks. Okay. So, normally we call it delta B, it is a base B system. So, B by B switches will be used in a delta B network, and if the number of stages will be k in this case, number of inputs and outputs will be b raised power k. So, that will be equal to n by n switch can be formed. So, delta B is basically subclass of Banyan. Now, how you are going to create it? In fact, if you must have observed that I actually made some changes here when I was drawing. If I go back to the original design, if I move it like this, if I now insert 0 0 0, it will still reach to the same outgoing port. You put 0 0 0 in any one of the input, it will always come to this one, does not matter. Put 0 0 1 or 0 1 0 from any input, you will always end up in the same output port there. Now, why this happens has to be understood. So, if you put for example 0 1 0, as I was telling, you put 0 1 0 here, what is going to happen? Since the first bit is 0, it goes up, next bit is 1, it goes down, it is 0, it comes here. Put from here, first bit is 0, it goes up, second bit is 1, comes here, third bit, it again comes here. What exactly is happening is, you can actually partition this into two halves. These two partitions are being identified by 0 and 1, the first bit. I can further partition this into two halves. So, first half is being identified by 0, second half by 1. And then they are being further partitioned depending on their port. So, it is 0, 0, 1, 0, 1, 0, 1, 0, 1. So, when I am actually selecting a 0 anywhere, I am invariably selecting whether it is going to the upper half or the bottom half. Now, to understand why this is going to happen, if I just simply swap these two, I just take this box and bring it down, I take this box and bring it up, it will immediately clarify what actually I am doing. So, if I do that, so I have to just do this rewiring. So, now you can clearly see when I am actually choosing 0, in both cases I am going to the upper half. If I am choosing 0, I am going to the upper half, choosing 1 going to this bottom half, this where the partitioning is happening between 0 and 1, just simply swapping this. Of course, this is the same structure which I had drawn earlier. If I just rotate it around, input becomes output and output becomes input. So, I am able to partition to 2 halves, and then depending on 0 I am going to either upper or bottom, the second division, same here, and the last one division will be happening within the switches, and that is the reason it is able to do a self routing, and this is delta 2 network actually. Delta 2 network of size of k is with k is equal to 3. So, 2 cube by 2 cube, which is 8 by 8, this is 8 by 8 switch. So, before moving further, let me just talk about how we will do the buffering here. So, as I told that for improving performance for this particular switch, one possibility is that I start increasing the transmission rate or link speeds, which is the speed up factor. We have done it in the crossbar, we can also do it in this place, that is one possibility. Second possibility is that because there may be contention, 2 packets trying to go to same port, I may provide one buffer at each one of the ports. This I do for every switch. So, when I am actually providing these buffers for every switch, this become buffered Banyan, or in this case it become a buffered delta network. Now, the problem is if 2 packets have come to this port, they both wanted to go to the same port, this one. So, one of them will pass through what we will do the other one if you keep it here and there is another packet being transmitted in the next cycle, when this packet cannot pass through or this buffer is not empty, then what you will do? One packet either has to be dropped, you are technically assuming that there will not be any flow from the back. So, we use something called a back pressure mechanism in this case. So, normally if this buffer is full, it will tell to the switch in the back that you cannot transmit to me because my buffer is occupied. So, if this is occupied, so any packet which is destined for this will not be transmitted further. So, it will be doing backward propagation. So, backward basically whenever a packet moves out, the signal will flow backward and the packet will move in the forward direction. So, no packet technically will get lost inside the switch, they can only get lost outside. So, there will be input buffers through which the packet will keep on moving. That is how the buffered delta actually operates. There is another way we can actually do it. These kind of conflicts, if these are because of internal links, if I can distribute the packets in properly, see in a random order. So, most of them, if these two are directing towards same port, if I would have put this packet somewhere here, it would have gone through the other link. So, internal conflicts can be avoided. So, that is done through a distribution network. So, randomizing and distributing. So, that is what is done through sorting and then distribution network. So, that is again a kind of Banyan network itself which does the distribution, randomization of the packet, so that internal link conflicts will not be happening. So far we have been assuming unicast, but in any internet switch or a packet or a packet router, I should provide a multicast capability. So, one packet goes in and multiple packets from multiple outgoing ports will be coming out. How that will be done? So, normally for that you actually have a small what we call a copy network which is put. The packets are being put and then each packet, how many copies have to be made, has to be inserted in the tag. As the packet goes through a small switch, it may take me, if it makes 2 copies, so it can actually put the half of whatever is the value in the tag here and remaining half here. So, as it goes along, more copies will keep on happening, ultimately this value will reach to 1. If it is an odd number, so say if it is 5, so you may put 3 here and 2 here. So there will be only 2 copies next time which will be made here. So when the copies are going to be made here, so 1 and 2, so next time there will be 2 copies being made by the next switch. So you will have 1, 2, 3, 4, 5 copies which will be created. So a copy network, a distribution network after this, okay, and then of course you will do a shuffle interconnection, and then putting a routing network, which is basically this delta network will give you almost this will give you non-blocking system with multicast capabilities, multicast as well as broadcast. If you do not need this, using these two only you will be able to do. This becomes a sorting network technically. Okay. So sorting plus this becomes a distribution network, and it will give you a almost non-blocking performance for the packet switches. So let us move to the analysis of delta network now. So how many networks, how many switches will be required, that is one important criterion. So if you are going to build up, now the trick for building delta network is very simple, that whenever you take a switch, all inputs which are coming to this switch should come from the same level of the previous switch. So if it is coming from 0 here and this being connected here, all these should also come from 0 only, from whichever switch, that does not matter. So far you do it, you will be able to create a delta network. But if you take from the 0th output this particular input, but from one output you take this one, then it will no more remain delta. Okay. So that is the only characteristic for a delta network actually. So we can try out, and of course if it is a B by B network, in that case you will require B outputs, and this will become B square next time, and it will be able to reach in the kth stage, the outputs will be B raised power k. Okay. And if this is also B raised power k, so for a switch which is n raised power B raised power k, there will be k stages. Okay. Each stage will require B raised power k minus 1, basically n by b, those many number of switches. So B raised power k minus 1 into k. So these will be total number of switches which will be required for a Banyan network or a delta network. Delta network, only this routing thing we have to take care of. Okay. And if you have A by B switch, then what is the condition? I can also build with A by B. So first stage will contain A, second one will be B. I can have, this basically becomes m by n, where m is equal to A raised power some number. So if it is a k stage system, so next output will be containing so these okay. So after the kth stage, let me just see how many of them. So my outputs will be B raised power k will be equal to n. So number of switches will be 1, B raised power k minus 1. Okay. So this will be 1, this will be A raised power k minus 1. Total number of elements inputs will be A raised power k. So m will be A raised power k, n will be B raised power k. So the number of output ports here will be now, I can write it here, A raised power k minus 1 into B. So these should be equal to these input ports. In a Banyan network or a delta network, which is subclass of that, none of these input ports will be left free and none of these output ports will be left free, and no input will be terminating on these internal input ports and output ports. They will be only, inputs will be coming here, output will be only going out from here, and since these are not free, so this same number of ports has to be there on this side. Okay. So I will take each one of these and connect, keep on doing it for every switch every time. Okay. And then on this side, number of switches now will be a raised power k minus 1 by b divided by, so this 1, this will be a raised power k minus 2b. So those many switches will be there. So first stage a by b switches, number of them will be a raised power k minus 1. Second stage a by b switches will be a raised power minus k2 into b. Third stage a by b and so on. So by the time we reach the last stage, which is the kth one, here you will be having b raised power k minus 1 switches. So total number of switches will be nothing but sum of these. So you can actually get a sum from here itself. So this is what you will get. When A is not equal to B, this is what is the total number of modules. When A will be equal to B, the number of modules will be these many. Okay. So, and of course we can actually see, take few examples and try it out whether self routing happens or does not happen. Only thing, this rule that all the inputs to a switch in a stage should actually come from the same level, same output port level of the previous stage switches should be taken care of, and you will be able to do the self routing. So the output ports may not be in the order, but those also always can be made in order by actually shuffling the output wires. So we can try out for example 3 by 2, 3 square by 2 square kind of configuration. So this actually means I will have 3 by 2, 2 of, so I need actually in this case 2 stages, so I will be requiring 3 square, so which is 9. And second stage I will be requiring 2 3 by 2 switches as per the construction. These are the outgoing ports. There will be only 2 stages, k is equal to 2, 3 inputs, 3 inputs. All these 3 should come either from 0 or they should come all from 1 level. So I can take all of them from 1, I can take all of them from 0. So this should be a self routing switch. You put from anywhere, now the kind of address which your tag which you will be putting will be what? It should be either 0 or 1. So, first bit will be 0 1, second will be 0. So, it is basically 2 digits, both of them will be binary numbers. So, if it is a by b switch, I will be using b-ary digit, k number of them, to identify the address of the outgoing port. Okay. So, in this case there will be 2 binary bits which will be there. So, for example, you want to put 0 0, you put from anywhere. If you put 0 0 here, the first 0 will cause the packet to come here, second 0 will come here. So, this is 0 0 output port. Take it from anywhere. So, if you take it from anywhere 0 0, it will, all of them will be coming here and ultimately onto this particular output line. Put says 1 0, in that case take it from any one of the inputs, one will cause it to go to the bottom and they will all come here, and then next one 0 will come and give a 0 here. So, this will be 0 0 0 1 1 0 1 1 and it is a delta routing network, it is a delta 2. But this is an asymmetric system, this is asymmetric network, but it is a delta network. So, we can actually have many kind of combinations, interconnections which can be done. But now the problem is I need something for a symmetric system, so that this interconnection can be replicated very easily when you do fabrication, when there are k stages. If I am not able to repeat this particular system again and again and again, every time I have to make a different interconnection pattern, and this is going to be, while fabricating, will become a difficult stuff. So, the question is, if I actually can make a switch of a by b, a by b, a by b switches, the interconnection pattern from first to second stage, second to third stage, third to fourth stage should be exactly same. And if I can do that, and that I should be able to build up still a self routing network. So, does that kind of switch is possible or not possible? Okay. But so far what we had done is, technically we call it baseline network. Remember, baseline actually has come, baseline or inverse baseline, both are self routing networks, they actually have come from Bain's network. So, remember, for a 4 by 4 the Bain's network which we had done earlier, this has come from reasonably non-blocking thing. So, this will be requiring 5 stages. So, there were 2 more stages, the full Bain's if I draw. So, remember, this was something like this. So, this is a baseline, this is a Bain's network. From the Bain's network, if I take only this particular part, these become the outgoing port, remaining I forget, this is a baseline network. And you can actually note, this is also a self routing system. You take this port, I am either going up or down, and then further from there only this is a self routing system. That is what actually I tried in the beginning. If I take not this one but the other one, other part is taking this onward all the way here, that is also a self routing network if you can actually carefully observe. Okay. So, if you put in, so both of them are self routing, but remember the interconnection pattern is not same, they are different in every stage. This one can be built through demultiplexer tree, the baseline one. The inverse baseline can be converted to this form by actually swapping the nodes here and there, moving them around. So, now question is, whether can I do it with uniform pattern between consecutive stages? Yes, we can do that. So, there is one particular network we call it shuffle. So, shuffle network actually does this. So, but for this we need to understand what is a shuffle interconnection.